went through what are the things you need. So you need to first of all decide about the left turning movement. It can be protected, permissive, or a combination. Then we need to decide about the lane groups, and you have to identify the lane groups in each approach. And lane groups are the lanes which have the same movements. Okay, and the rest of the calculation is done for each lane group. Okay, so you have to calculate the demand volume and saturation flow rate for each lane group. Then you come up with the phasing plan. So in the phasing plan, you try to minimize the V by S ratio. So each approach will have the saturation flow rate and the demand flow rate. Okay, so you will take the V by S ratio for the lane group in that approach, and you will add them together. Okay, so maybe one lane group has a V by S ratio of 0.1, the other one has 0.3, the other one has 0.05. You add them together. Okay, and it should not be more than 1. More than 1 is impossible. Okay, you cannot do that on a signal then. Okay, because saturation flow rate is not even capacity, it's more than the capacity. Okay, so if you are getting V by S ratio more than 1, that means it's impossible to design a signal. There is no possibility. So even they are saying 0.9. If you go to up to 0.9, it is maximum. Okay, so design the phasing plan so that you get minimum summation of V by S ratio. Okay, up to 0.9 is allowed, but less is better, like your grades. Okay, then we have the movement coding. Okay, so state movements coded with even numbers. Okay, and the left turnings are coded with odd numbers. Okay, and the right turnings are coded with 10 plus numbers, and the pedestrian movements have a P with them. Okay, so you can know from the number which type of movement it is. Then we calculate the yellow and all red time, which is basically for the people who are in the dilemma zone. What is the dilemma zone? Anyone?
There is a problem.
Huh? There's a problem, yes. There's a problem that you didn't come yesterday. What is the dilemma zone? Not too close, not too far from the signal. If you are too close, obviously, there's no stopping. There's no chance of stopping for you. Huh?
This is a problem.
This is a problem, yeah. You keep on missing classes is also a problem. Okay. And too far, obviously, then you see the yellow, you know that once you reach it will be red. So you already made up your mind that I have to stop. The people in the dilemma zone, some of them will try to go, some of them will stop, and we give the yellow and all red time for these people to clear the intersection, not only enter. Get my point? The purpose is this guy enters, and the next one has green. My problem is still there. This guy is now in the middle of the intersection. Okay, so the yellow and all red should be for the guy who is in the dilemma zone to clear the intersection. He should reach the other side. Okay, and this should happen between yellow and all red time. How do we calculate it? We calculate it from here. Okay, so you see the long equation here. From this equation, this part is for the yellow time. Okay, and how did we get this? We took the equation of stopping sight distance. Okay, which you learned when you were kids. Yeah, like 4 or 5 years. Okay, right? So in a school with Dr. Rashid. So we took the equation of stopping sight distance divided by the speed to get the time. Okay, so this is for those guys who are exactly at the stopping sight distance from the signal. Okay, so we consider it a dilemma zone. So these people decide to go. Okay, so during yellow time they will reach the stop line. Okay, they reach the stop line, and then they will have, so these guys, they decided we will go. Okay, they decided we will go. So then you have the other time for them, the other part, this part, to help them clear the intersection. Okay, so let me take it from here. So from here to here they will reach in yellow. expecting the worst case. The worst case is the person who had the stopping sight distance from the signal, even he decided I will not stop. Why should I stop? The world should stop for me, right? So he decided he will stop, so he will, obviously he is insane, so he will reach until the stop line, okay, but he is still moving, he's not stopping, okay, so he will continue, okay. So when he is here, the all red started, okay, and then he realizes the world doesn't stop for anybody, and you should realize it as well, okay. So the all red started, but he's too fast, he didn't decide to stop, so he will keep on moving. So all red is enough for him to go from here with his car and reach the other side completely. Completely meaning that his car is on the other side now. There is no part of the car which is in the intersection, okay. So this is how we get this. You see, W is what? The width of the intersection, this part. And L is what? The length of the car. Okay, so the car will completely go to the other side. Okay? Okay. And S naught is the speed, obviously. What is small g? 9.81. If it is anything else, you will get 0. In feet per second, it is 9.8.
No, it converts.
Convert. What is it? Gravitational acceleration. See, a scientific answer. You were saying what? 32.3. See? Who needs what? Who needs to know when we have the value? Huh? Whatever it is. 32. It's 32. Huh?
Engineer, doctor, not
Eng-
science. Not scientist.
The whole one. You are not even an engineer. Okay? See, he is trying to on WhatsApp. He is trying to become an engineer on WhatsApp. Okay?
I fight for that.
Very
5
good.
years I'm in.
Huh?
5 years I'm in. I'm fighting for this something. So
Keep going for next 5 years.
ridiculous something.
Okay. A is a deceleration. We have deceleration of the vehicle. We have a value for that. Okay, and so on and so forth. This equation gives you a minimum. The actual can be more than this. Okay, the equation gives you minimum. The actual can be more than this. But keep in mind, the first two terms are minimum for yellow. The last term is the minimum for all red. L is the length of the vehicle. We have a standard for that as well. Capital G is a gradient. Okay, of the road from where the vehicle is coming. Okay. Then we need to calculate the lost time for every cycle, for every phase. Okay. We have discussed this in the last course as well. There are two lost times. In every phase, there are two lost times. Okay. One, we already mentioned. Okay. This one. This one is what? What is AR? All red. This is a lost time. All signals are red, right? So it's a lost time. Okay. Then we have another lost time, which you can see in the graph here. Okay. The headway between the vehicles. Okay. So if you are looking at the signal on the stop line, you are looking at the stop line of the signal. Okay. So you will see that when the first car moves, it moves slowly because it was right at the stop line. The next one will be faster, and the next one will be faster. So when the cars are getting faster, their headway or their interval is getting what? When the cars are getting faster, their headway is getting what? Less. They're becoming faster, right? So they're coming close to each other now. Okay? So the headway is coming less and less and less. Okay? But the first 3-4 cars took some extra time. This extra time is also lost time. Okay, this extra time is lost time because the actual minimum is what? This one, right? The actual minimum is this one. Okay, so the extra time is also lost time. This happens in every signal. This one is called startup lost time, and the other one, AR, is called as clearance lost time. So every phase has a clearance lost time and a startup lost time. Okay, so They have given us some recommended values that you can take the total of both startup and clearance to be 3 to 4 seconds. Okay, startup can be taken as around 2 seconds. Okay, plus clearance of 1 to 2 seconds. But I can calculate the clearance exactly, right? I can calculate the clearance loss time exactly. Where is it? The all red time. Okay, so you can calculate the all red time exactly, the clearance time, and then you can add the 2 seconds of startup loss time. Okay.
Also, Doctor, yellow is lost time. Yellow.
Sorry.
Only all red is lost time or also yellow.
No, some part of yellow is also lost time. This is for people who are behind the dilemma zone. Okay, so they decided they want to stop. Okay, so they decided they stop. Okay, so they came close to the intersection. Signal was yellow, still yellow. But since they decided to stop, obviously now they will not accept it. So they will eventually stop. So some part of yellow is also part of clearance. Some part of yellow is also part of clearance. Okay, but anyways, we have the recommended value for L1 and L2. These are given here. The total is 2 plus 2 or 2 plus 1, 3 to 4 seconds. Okay, 1 second for clearance and 2 seconds for the 1 to 2 seconds for clearance and 2 seconds for the startup loss time. But if you want to measure it, you can go to the signal and you can measure these things. Okay. So we have a phase. A phase comprises of 3 things: green, yellow, or red. Okay. This is the time in which a movement is allowed. Okay, a particular movement is allowed, because other movements during this phase, no other movement will have green. Okay, so this is the time for one movement. Only that movement is going on. It is clearance for who? For this movement. Even if it is all red is used by who? Clear who? This one. These people. Okay, so phase time is the total time which you are giving to the movement, and no other movement will have green during this time. Okay, from the phase time, if you subtract the loss time, you will get something which we call it effective green. Okay, so phase is green plus yellow plus all red. You add these 3, you get the phase. From these 3, you subtract the loss time, you get effective green. Okay, and what is happening in effective green? The vehicles are going at minimum headway, minimum interval. Okay, so effective green is the time during which vehicles are crossing the stop line at minimum headway. Got it? Okay. Okay. Yeah. Then, so if you have the loss time for every phase, you can add all of them, because a signal will have more than one phase, right? It has more than one movement. Okay, so if you add the loss time for all the movements, you get the total loss time of the cycle. Okay, so every phase has a loss time. You add the loss time of the phases, you will get the loss time of the cycle. Clear? Okay. There can be some signals where the phases are overlapping. You are allowing 2 movements at the same time. For example, 2 straight, eastbound and westbound. They can be allowed together. Okay, but these are 2 different phases. Okay, allowed together. So these are overlapping, right? Happening together, overlapping. So this one will have a loss time, and this one will also have loss time. Since they are happening together, I will not add this plus this. Just, okay, I will take one of them. If they are different, I will take one of them and just add that one. That's it. Okay, so for overlapping phases, the loss times becomes combined. Okay, so you don't have to add for both the movements, both the phases. You will take one, and obviously the one which should be maximum should be taken. Okay, then we select a volume to capacity ratio. Okay, a target volume to capacity ratio. Now I explained earlier as well, we have a V by S ratio, volume to saturation flow rate ratio, and we have a volume to capacity ratio. What is the difference between them? Volume to saturation flow rate, volume to capacity. What is the difference between capacity and saturation flow rate?
But
Does
still
not
you move
include
with
the
the
stop.
Mhm.
Does not include the stop.
Which one?
capacity.
Capacity does not include?
Saturation flow rate without delay or stop.
Yes. Saturation flow rate is imaginary, hypothetical. Okay, so it does not include stopping. Okay, so that's the
Yeah.
difference.
They are slow, very slow.
Huh?
But they are very slow,
Oh, it's very slow.
the saturation.
Saturation is at minimum headway. At minimum headway.
Speed doesn't not affect.
Speed doesn't matter because the interval, we are measuring from the interval. Okay. So saturation flow rate does not consider the stopping. Capacity is actual capacity. Okay, with the red and the lost time and everything. Okay, clear? Okay, so previously we were talking about V by S ratio, and here we are talking about V by C ratio. Again combined for all the approaches, combined. Okay, so total volume upon total capacity of the intersection, not lane group. It's not for lane group, total. Okay, and you have to decide. You have to decide. Okay, can I take any value, volume to capacity, any value is possible? 2, 3, 4, 1 million. Can I take any value? Volume to capacity should be what? Which one should be more, volume or capacity?
Capacity.
Capacity should be more, right? So the ratio should be
Less than
less than 1. Okay. Even 1, like I mentioned, is considered ideal in this case. That means you are not giving any unnecessary extra time to any movement. Okay. But that also means what? No volume to capacity ratio exactly 1. Exactly 1. What's the problem with that? The good thing is, okay, I'm not wasting any time. I needed 60 seconds, I'm giving exactly 60 seconds.
If
Good
there
thing.
is any problem, they will die.
There is no factor of safety here.
Maximum
Okay.
flow.
Maximum flow is exactly equal to capacity. Okay. So there is no factor of safety here. So that's why we take it less than 1. We keep a margin of 10 to 15%. So at the actual ratio is taken as 0.85 to 0.9. If you are using sensors, then you can take a higher value. If anything unexpected happens, the sensor will take care of it. But even in that case, we don't go up to 1. But you can go more than 0.9 with the sensor. Okay. But this is the value which needs to be decided. It's not calculated, you will decide how much. Okay, then we can calculate the cycle length. This is the equation which we have used previously as well in the previous course. So this is the equation which comes from the lost time. Okay, and this is the equation which they came up with somehow. Okay, it's an empirical equation. So Mr. Webster, he was sleeping a night, and when he woke up, he just came up with the equation. Okay, so capital L means the lost time. XC is the volume to capacity ratio. XC is the volume to capacity ratio, which you have decided. Okay, and V by S, volume to saturation flow rate. Okay, which you have calculated. And while we are doing the summation for each phase. Each phase will have a lane group, and that lane group will have V by S ratio. Clear? Okay. Any questions? So you can have two different values of cycle lengths. The range is from 40 to 180 seconds. 180 seconds means how many minutes?
2.5.
3.
Three. Okay. 3 minutes. Okay. Because if you make it too long, okay, the equation, let's say the equation comes up with the answer 10. It can come. Okay. Like some people come after 20 minutes, the equation can give an answer 10. Okay. But the problem is with that is what? 10 minutes for the whole cycle. So if you missed your green, then you will have the next green after 10 minutes. Okay. So which is a very, very long time. Okay. So that's why to make the cycle length reasonable, we have some ranges. Okay. But this is the range according to the book. The local standards can be different. Okay. Like you may have signal which have more than 3 minutes of cycle length. Okay, so you can go to the traffic director, tell them Dr. Vinayam is telling us not more than 3 minutes.
7 minutes.
Okay,
And there is a signal 7 minutes.
there's a police officer which stops me for 10 minutes in the morning. I don't go from that signal. That way is like a shortcut, but I know if I go there, it will, they forget about it. When they are standing there, they will stop you and then they will stand like this. So they don't even see you. Okay, so anyways, what I was saying, yeah. So apply the local standard for minimum and maximum after you calculate the values from here. And if your value is more than the local standard, you will go with the one which is in the standard. Okay, but that also means you have to back calculate then how much volume capacity ratio you can have and so on. You may have to change the things. Okay, yeah, once you get the value, you have to do some rounding off. Rounding off is usually to the nearest 5 or to the nearest 10. Okay, depending upon, they have given us a range as well. If it is less than 80 seconds, you can round off to the nearest 10. Okay, so for example, if it is 71, you can make it 80. If it is 62, you can make it what? 70. Okay, but if it is more than 80, then we round it off to the nearest 5. If it is 81, you don't make it 90. Make it what? 85. Okay, clear? If it is 96, then
70. Oh, 96, shit.
100.
100 maybe. What do you want to tell?
yes,
He's not late. and
not
he-
him. How much will it be?
جاوب ما
182 جنب
ما نشغل.
See, he doesn't even know the question. 80.
80 بس ولا لا؟ If it is more than 80, we make it 81, 85, 9600. Yeah, لا? No need to be chemical here. I already understand.
Obviously,
فتح البرنامج.
you're already late by 2 years. Okay, so anyways, you cannot round down. Okay, you cannot round to the nearest 5 downwards. Okay, what else? Okay, from the cycle length, whatever you decide, the total after rounding off and doing everything, you decide the total cycle length. Okay, from the cycle length, you subtract the total lost time, total for the entire signal, you will get total effective green. Okay, you get total effective green. How do we get effective green? Effective green means what?
Useful.
Green time minus lost.
Green time minus lost time?
Green plus yellow plus orange.
Yeah, phase time minus
Minus.
lost time. Okay, so this will give you total effective green for all the phases. Okay, so for example, your cycle length is 120 seconds and your lost time for every phase is 4 seconds. Okay, and we have 4 phases. Okay, so how much is my effective green? Tell me. 120 seconds of cycle length, 4 phases, and every phase has a lost time of 4 seconds.
104.
So how much is the
104.
104? Yes. So total minus lost time of one phase multiplied by the number of phases, because all, according to them, all phases have the same lost time. Okay, so it will be 104 seconds. Then you can calculate G by C ratio. Effective green upon cycle length ratio. So for this case, how much will it be? 120 seconds of cycle length, effective green 104 seconds. So how much is the G by C ratio? 0.87. Okay, this G by C ratio should be more than the summation of V by S ratio. Volume to saturation flow rate ratio. Okay, if it is not, that means again the design is not possible. Okay, G by C ratio should be more than volume to saturation flow rate, summation of volume to saturation flow rate ratio. Okay, clear? This ratio increases, capacity of the signal increases. This ratio decreases, capacity decreases. Okay, G by C. Clear? Yes.
Okay, 120 minus 4, then we multiply with 4.
Because 4 phases. 4 seconds of lost time every phase.
Then we multiply the whole thing with 4, right?
What whole thing? No, we are only multiplying 4 with 4.
Okay.
Okay, once you have calculated the total effective green time, then you can calculate the effective green time for each phase, for each movement. Okay, so C minus L is what? We did it. C was cycle length, L was lost time. It will give you what? Total effective green. Okay, so we are dividing total effective green according to the V by S ratio. Okay, so this is the V by S ratio for this phase, and this is the total V by S ratio. Okay, so total effective green multiplied by V by S ratio of this phase divided by total V by S ratio. Clear? Any questions? Okay. Now we know that phase minus lost time gives me effective green, right? Phase minus lost time gives me effective green. So that means phase equals to green plus lost time. Clear? Huh? Clear now?
No idea.
Okay. Effective green equals phase, green plus yellow plus all that, minus lost time. Okay. So this was green plus yellow plus all red minus lost time equals to effective green. Okay. So now I take the lost time on the other side. So this equals to this. Why did I do this? Because effective green I already calculated. Lost time I already know. I want to know what? The phase time. Okay, so this equation will give me the phase time. Okay, I already have this side of the equation, I want to know this side. Now in this side, we have an equation for two things, which on this side. I have equations for two things. Which ones? Yellow and all red. I already have the equation. I already calculated this time. Okay. So now only remaining thing is what? Green. Okay. Clear? So this one, effective green, comes from the cycle length. Last time we already have discussed. Okay. We have standard values for that, and we can measure it as well. Okay. So using them, I can calculate the phase. From the phase, these two have an equation. So I can calculate then the green. Clear? This is the actual green when the signal will show green light. That's why we need to know. Okay? Effective green is just for us. Okay? The driver doesn't know about effective green or something. We need to tell the driver or the programmer when the signal should become green. The light should become green. Okay? So that's why we are doing this. Clear? Okay, they have some minimum values here. The minimum value says that for the major street, the green should not be less than 15 seconds. For minor street, it should not be less than 7 seconds. When the signal becomes green, okay, it should remain green for at least 7 seconds for the minor road. Okay, and for the major road, should remain green for at least 15 seconds. Less than this will be too sudden for the driver. Okay, like he will feel the signal became just green and then again yellow. Okay, so it will not give him enough time to react. Okay, so these are, any value less than this is not practical for the driver. It will be too sudden. Okay, some of you have done the speed studies, right? The speed study for the project, right? Okay, if you did it using the time, you can, 2-3 seconds the car will move and you will not even know it. Okay, so we have some practical restrictions. Then the last step is to check for pedestrians. The timing which you are giving on the signal, is it good enough for the pedestrians to cross as well? Remember, we are talking about signal which is designed for the vehicles. So our main concern is not pedestrian. So we calculated everything using the traffic volume and the traffic data. Okay. Now we are coming to the last step just to see if a pedestrian is there and he decides to cross during the red time, is it enough for him or not? Okay. Now if the pedestrian is crossing, he will cross with which movement? If I am crossing in this direction,
Parallel movement.
the parallel movement. Okay. So you will check the pedestrian required time with the phase time you are giving for the parallel movement. Okay. So I am crossing in this direction, and this movement also has green. So I can only cross in this time, right? Okay. When the car is going with me. Okay. So is this time enough? Maybe it's enough for the car, but not for me. Okay. So we need to check these things. First of all, I should know how much time the pedestrian will need to cross. Okay. To calculate the minimum required time for the pedestrian, we have this equation. Okay. The equation has two parts: the walking time and the flashing what? Flashing don't walk time. Okay. So like we have the flashing green, right? Flashing green means what?
3 seconds then will
You measured it. Very good.
duration time and they will turn red.
So it means the signal is about to turn red. Okay. So it means the same thing for the pedestrians as well. Okay. So we have a pedestrian flashing time as well, in which the pedestrian is giving the indication that signal is about to close, so you have to hurry up. Okay. So we have the walking time and we have the flashing time. Okay. In the flashing time, he has a warning now. The signal is about to close. Okay. For the walking time, for this time, the flashing time, we have the speed, the normal speed of the pedestrian, or not the normal, 15th percentile speed of the pedestrian. Okay. Width of the intersection divided by this speed. Okay. So again, he saw the flashing, but he said, no, I have to go. Class is more important, I can die for it. Something like this. Okay. So he decides to go, then the flashing time is enough for him to clear the intersection again. Okay, the width and the speed of the pedestrian. For walking time, we have some values here. Where is it? 5 to 7 seconds. Okay, but you can calculate the value using the same thing with a lower speed, because it's not flashing, right? So his speed is normal. This is more than normal. Okay, because he knows the signal is about to close. Here he will be going at, or you can assume that he will be going at a slower speed. Okay, so maybe you can add 0.5 feet per second here and calculate this time as well. Okay, if you know the width of the intersection. So this can come in the same way. Clear? Okay, but they have given us a value. Again, these are minimum values. Okay, and mainly required for minor side streets. People who are coming from the minor street, they want to cross the major road. Then there's a problem, right? Major road is bigger, so they need more time. The minor street, usually traffic volume is too low, and even if they decide to cross, the time for the major road is too high, so they can cross easily. Okay, so okay, we have been giving with this example. You can see the lanes here. Okay, how many lanes are there? How many movements are allowed? And then you can see the speed limit here. Okay, and you can see the information here for the median and the lanes and terrain. 0% trucks, 0.95 is the factor for peak hour. Okay, and these are the volumes for which we are doing the design. Okay, so the data which is given. first thing we need to check if the left turns are protected or permitted. Okay, if the left turns are protected or permitted. Now here they say the left turns are protected, and the reason is okay, if the road has a speed of 45 miles per hour or higher, then you should make the left turning protected. Okay, if the road, the main road or any road has a speed of 45, the opposing road. Okay, so I'm taking the left turn and it's coming from this direction. So if this road has a speed of 45 miles per hour or higher, then you should make the left turning protected. Clear? Okay, so in the example they have the road which has a speed of 45 miles per hour or more. Okay, so that's why the left turnings are protected. So the first thing is done. The next thing is, okay, we should identify the lane groups. Okay, now look at, so they are similar, right? These two are similar. Okay, how many lane groups I have here? 2, right? They cannot be in the same group because they have different movements. Okay, I have 2 lane groups here. What about this one? How many lane groups here? Again, they are similar. So whatever you say here would be applied here as well. 3, right? The 3 lanes and all of them have some different movement. Clear? So these two have a common movement, so they can be in the same movement group. So now when I will design the phase, I cannot design a phase for this lane and this lane separately. They cannot be separated, right? These 2 lanes cannot be separated. Can I make them separate? Yes. There is no common movement, right? So I can have a phase for this one, I can have a phase for the other one as well. Okay, so this is how it helps you. But anyways, I have 2 lane groups here and I have 3 lane groups on in the east-west direction. Okay, for each lane group, now I have to decide the demand volume. Okay, now you can see the volume is not given according to lanes. The volume is given according to movement. Okay, so for example, if I'm talking about this lane group, this is only for left turn. So what is the volume of left turning? 150. Clear? Okay. This one, left turning. What is the volume for left turning? 150. What about this one? This is for straight and right? Both, right? Okay. So this one will have 300 plus 50. This one again is straight and right. So this one will have 350 plus 50. Clear? Okay. Same thing here. This one will have only for left turn. This one will have straight. This one will have straight and right both. Okay. Now the problem here is what? How many movements for straight here? How many volumes? 1. Okay. So some of it will be in this lane and some of it will be in the other lane, right? Because both lanes have this movement. Okay. So then we have to decide how will we divide this volume? What percentage? Okay. So what percentage of it will be from this lane and from this lane? Similarly, if I had 2 lanes for left turning, if I had 2 lanes for left turning, then I have to decide how much from each lane. Okay, so whenever you have more than 1 lane for the same movement, you have to decide the percentage. Okay, and you cannot say it's equal. It's not equal, right? Practically, we don't see traffic dividing equally in 2 lanes or 3 lanes. Okay, there is always some unequal treatment. Okay. In this example, they are saying, okay, we will divide it 45%, 55%. One lane will have 45, the other one will have 55. Now, which one will have more? Both are
The middle one.
the middle one. Okay, because this is only for straight. This one has a shared movement. Okay, so people obviously will try to avoid this one and go in this one. Okay, so but the number, this is the logic. Okay, so if you have two lanes, okay, one is shared and the other one is only for straight, then more people will go towards that lane. This is logic. But how much? This is given in the book. Okay, or you have to observe it. Okay, so it's not always 45-55. It could be 40 and 60 as well. Okay, but for this question they are saying, okay, it's 45-55. So this lane will have 55 of 550. This lane will have 45 of 550 plus 50 for the right turn. Clear? Okay? And same thing for the other side as well. Okay? So this is how we will calculate the volume for each lane group. Okay? So first of all, what did they do? They divided each value with peak hour factor. The values were given as volumes. The given values 150 and 50 and 550, they were volumes. You divide by peak hour factor, they become what? Flow rate. Okay, they become flow rate. So first thing is you calculate the flow rate if it is not given. Okay. One more step which was not required here, that was the factor of heavy vehicles. Okay, here I have 0% trucks and level terrain, so factor of heavy vehicle is not required. 0% trucks, factor of heavy vehicle is not required. If it was required, you will divide it by the factor of heavy vehicle here. Okay, so if I tell you 2% trucks, so for 2% trucks you will calculate the factor of heavy vehicle, and then you divide by peak hour factor and the factor of heavy vehicle. Okay, in the end we need flow rate in passenger cars. Okay, here I need flow rate in passenger cars per hour. Got it?
So you got percentage of the truck.
You have to calculate factor of heavy vehicle like we did in the previous chapter.
After I calculated, remember about peak hour factor plus?
Not plus, divide again.
Divide and okay.
Yeah, divide by both. Peak hour factor is how much was it? 0.9 something, and let's say your factor of heavy vehicle is 0.96. So 150 divided by 0.95 and again divided by 0.96. Clear? Okay. So the first thing you do is convert the demand into passenger cars per hour flow rate. Okay, divide by peak hour factor, divide by factor of heavy vehicle, and so on. Then the next thing you do is calculate the flow rate for each lane group, like I explained. This is for each movement, right? Left, through, and right. Left, through, and right. Okay. Now you look at the lane groups and calculate the flow rate for each lane group. Okay. So lane group number EB1, let's say, or NB1. NB1 is this one, this lane, which is going left. So it will only have the flow from the left turn. Okay. NB2 is taking what? Right and through both. Okay. So for NB2, I will add these two values. Okay. Clear? NB2 is this one. Okay. So through and right. Added. Clear? Okay. So first you should identify the lane groups. Then you should know how to divide the volumes and so on and so forth. Now WB2. WB2. Okay. So total through was, where is it? Total through is 579. Okay. 55% will go in WB2. Okay. So 579 into 0.55 gives you 318. Okay. And then WB3 is this one and the right turning. Right turning is 53. Okay. And how much is this? 45% of 579. Clear? Okay. So this is the next item. Now, this one, saturation flow rate. How to calculate saturation flow rate, how to calculate adjusted saturation flow rate, we have already covered. Okay, just trust me, we did. In this course, in the same slides. It's there somewhere. Okay, in your childhood. Okay, we did. Okay. For the example, they already gave us the values. But if they don't give us the values, then we have to calculate the saturation flow rate and we need to apply the adjustments. Okay. So these are the saturation flow rates which are given for each lane group. Okay. So now we will calculate for each lane group the V by S ratio. Okay. V is the demand flow rate for each lane group and S is the saturation flow rate. So this upon this 0.09, this upon this 0.19, this upon this point something something. Okay. Now I need the summation of V by S ratio. How much is the summation of V by S ratio? Tell me. Add all of them. Add the last row. Complete.
I think it will be 1.5 something.
0.43.
Huh?
I got 1.43.
1.7 now.
1.7.
Yeah.
You cannot trust anyone.
1.7 now.
1.79. Okay. Now we will do the phasing plan next time. But what does it mean? 1.79. That means your volume is more than the saturation flow rate. The total volume, the total demand flow rate is more than the total saturation flow rate. This is what it means. Okay. It also means that you cannot design a signal which has a separate phase for each lane group. Okay. Now how many lane groups we have? Can you count? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Okay. So I cannot have a 10 phase signal here. 10 phase means what? Okay, this one will have a phase. This one will have green, separate. Separate green for this one, then this one, then this one. It makes my life easier, right? Just take the movement and put a green there. Put a signal for that. Okay, but this one tells me it will not work. If you do this, your total demand is more than the total saturation current. So you cannot do this. Clear? Now we have to overlap some of the movements together so that the summation of V by S ratio becomes less than what? Summation of V by S ratio becomes what? Less than 1. Okay, or even less than 0.9. Clear? Okay, how do we do this? We will discuss it next time.